Hello everyone. Today we will study the fundamental theorem of calculus. Before I introduce what it is, let's look at some problems first. Simplify each of the following expressions. First expression is the derivative of the integral from 1 to x 6t squared dt. For this expression, we take the definite integral first, and then take derivative. So let's do the definite integral first. Integral from 1 to x 6t squared dt. How do we solve this integral? According to evaluation theorem, take antiderivative first. I get 6t cubed over 3, and then evaluate from 1 to x. If I simplify 6t cubed over 3, I get 2t cubed from 1 to x. Next, we plug in the upper limit, plug in the lower limit, and take the difference. If I plug in x, I get 2s cubed. If I plug in 1 cubed is 1, 2 times 1 is 2, so I get 2s cubed minus 2. That's an answer to this definite integral. Next, we take derivative. Take derivative for 2s cubed minus 2. Here we can use power rule. Bring 3 to the front, I get 6x squared. This number 2 is a constant. When I take derivative for constant, I get 0. So the answer is 6s squared. That's how we simplify this expression. Next problem. How do we simplify the expression? Derivative of the integral from 0 to x sine t dt. For this expression, we take the definite integral first, and then take the derivative. So let's take the definite integral first. From 0 to x sine t dt. According to evaluation theorem, we take an antiderivative of sine t first. Antiderivative of sine t is negative cosine t. Evaluate from 0 to x. Then we plug in the upper and lower limit and take difference. If I plug in x, I get negative cosine of x. If I plug in 0, I get negative 1. If I plug in 0, cosine 0 is 1, so I get negative 1. If I simplify, this expression is 1 minus cosine t. One minus cosine x. Double negative is positive 1, so I get 1 minus cosine x. That's the answer to the definite integral here. Next, we take derivative. Derivative of 1 minus cosine x. Derivative of 1 is 0. Derivative of cosine is negative sine. Double negative is positive, so the answer is sine t, is sine x. Next, derivative of the integral from 1 to x square root of 1 plus square root of t dt. How do we simplify this expression? In this expression, we must take the definite integral first, and then take derivative. How do we take definite integral here? This integral looks very, very complicated. It doesn't look easy. But can we guess an answer? Based on the first and the second example, can we guess for the answer here? Can we guess for the answer? We can't take this integral here, but can we guess an answer? Can we guess an answer? Observe the first and second example. Can we guess an answer? In the first example here, 6s squared looks almost the same as 6t squared. The only difference is we plug in x for t. In the second example here, sine x looks very similar as sine t. The only difference is we plug in x for t. So it looks like the derivative undo the integral, it go back to 6t here. The derivative undo the integral, it go back to sine x here. If that's correct, the derivative will undo this integral here. I plug in x for t. So by guessing, the answer is square root of 1 plus square root of x. That's by guessing. Is this true? Next, let me introduce the fundamental theorem of calculus. The fundamental theorem of calculus, sometimes we write it as FTC. It says, suppose f is continuous on the interval from a to b, then the derivative of the integral from a to x, f of t dt equal to f of x for all x in the interval from a to b. So this theorem says the derivative of the integral in the form that lower limit is a constant, upper limit is x, f of t dt. For the derivative of integral in this form, we plug in x for t. We plug in the upper limit for t, like f of x. If the lower limit is constant, upper limit is x. When I take the derivative with respect to x, I plug in x for t. Answer is f of x. Plug in s for t, we get f of x. So, according to the fundamental theorem of calculus, let's look at this example here. That's the derivative of integral from 1 to x. Lower limit is a constant, upper limit is x. When we take derivative with respect to x, we plug in x for t. Plug in x for t, I get square root of 1 plus square root of x. Plug in x for t. So this is true by fundamental theorem of calculus. This is true by the fundamental theorem of calculus. So when we take derivative for integral, if the lower limit is a constant, upper limit is x, then we plug in upper limit for t, which says derivative undo the integral in this form. The derivative undo the integral in this form. We plug in upper limit for t. Derivative undo the integral. Derivative undo the integral in this form. We plug in upper limit for t. The derivative undo the integral. We plug in upper limit for t. That's what fundamental theorem of calculus says. Next, let's prove the theorem. First of all, let me create a new function called g of x. The g of x in this integral from a to x f of t dt. For all x in the interval from a to b. Then g prime of x can be written as derivative of this integral from a to x f of t dt. If this integral is g, then g prime of x is the derivative of this integral. So for this theorem, all we need is proof g prime of x equal to f of x. For this theorem, all we need is proof g prime of x equal to f of x. Now let's try to prove it. First of all, let me recall the definition of derivative. Definition of derivative says f prime of x equal to the limit as h approaches to 0, f of x plus h minus f of x over h. That's what we learned last semester. So let me apply here. By the definition of derivative, g prime of x can be rewritten as limit as h approaches to 0, g of x plus h minus g of x over h. That's the definition of derivative. Next, let's simplify this expression here. What's g of s plus h? For g of s plus h, go to function g. Replace each x with s plus h. Go to function g. Replace each x with s plus h. So I get integral from a to s plus h f of t dt. minus g of x. G of x is integral from a to x. F of t dt over h. That's a numerator. Now, how do we simplify this numerator? Integral from a to x plus h, f of t dt, minus integral from a to x, f of t dt. Definite integral represents area under the curve. Definite integral represents area under the curve. So the first integral represents, let me draw a graph first. Suppose this function f is continuous from a to b. X is somewhere between a and b. Suppose this is h. Suppose this distance here is h. Then this point will be s plus h. First integral from a to s plus h, f of t dt, from a to s plus h. First integral represents area under the curve from a to s plus h. That's the first integral. Area under the curve from a to s plus h, f of t dt. Second integral from a to x, f of t dt. It represents area under the curve from a to x. Second integral represents area under the curve from a to x. Second integral represents area under the curve from a to x. First integral represents area under the curve from a to s plus h. Second integral represents area under the curve from a to x. If I subtract, what do we get? If I take the total area, take away this area, what's left is this area here. And this area here is what? That's area under the curve from x to s plus h. This is area under the curve from x to s plus h. What we have here is area under the curve from x to s plus h, f of t dt. So if I take this integral minus this integral, what's left is this integral. So that's how we simplify the numerator. So the numerator is the integral from x to s plus h, f of t dt, all over h. Next, let me recall the extreme value theorem, EVT. That's what we learned last semester. It says, suppose f is continuous on a closed and bounded interval AB. Then there exist real numbers CD in the interval AB, such that f of c is an absolute minimum and f of d is an absolute maximum. So extreme value theorem says, if f is continuous on a closed and bounded interval, then it has an absolute maximum and absolute minimum on the interval. That's what extreme value theorem says. Keep it in mind. Now, consider this integral from x to s plus h, f of x, f of t dt. We are looking for area under the curve from x to s plus h. Since f is continuous, on the interval AB. Since f is continuous on the interval AB, then f is also continuous on the interval from x and s plus h. Assume the interval x, s plus h, is a subset of the interval AB. If function f is continuous from a to b, then the interval x and s plus h belong to the interval AB. if f is continuous on an interval ab, it must be continuous on a subinterval from x to s plus h. This is a subinterval. It must also be continuous. If the entire piece is continuous, this small piece must be continuous. Then, by the extreme value theorem, there exist real numbers c and d in the interval from x and s plus h. There exist real numbers c and d in the interval x and s plus h, such that f of c equal to small m is an absolute minimum. And f of d equal to big M is an absolute maximum. So extreme value theorem says, if f is continuous on the interval from x to s plus h, then on this closed and bounded interval, there exists absolute maximum and absolute minimum. In this closed and bounded interval, there exists an absolute maximum, absolute minimum. Let's call small m to be an absolute minimum and big M to be an absolute maximum. Small m occurs when s equal to c. Big M occurs when s equal to d. Since small m is an absolute minimum and big M is an absolute maximum on the interval from x to s plus h, then for this integral here, between x and s plus h, f of t, it must be between small m and big M. So f of t must be between small m and big M, since that's the minimum and that's the maximum for all t in the interval from x to s plus h. Next, let me recall a property of integral. That's what we learned in the earlier section. It says, if f of x is between small m and big M for all x in the interval from a to b, then the integral from a to b f of x dx is between m times b minus a and big M times b minus a. That's a property we learned in the earlier section. That's applied here. So, since f of t is between small m and big M on the interval from x to s plus h, if we try to match the formula here, x represents a, s plus h represents b. So if we apply the formula, by a property of integral, integral from x to s plus h, f of t dt is between small m times b minus a. That's b, that's a. And big M times b minus a. That's b, that's a. If we simplify here, on the left side, x can cancel. We get mh. on the right side, also h can cancel. We get big M times h. Now observe this limit here. We have this integral x to s plus h f of t dt over h. I try to add h on the bottom here, which means I can divide all three parts by h. I can divide all three parts by h. If I divide all three parts by h, I get small m is between integral x s plus h f of t dt over h and m. Divide all three parts by h. Here, small m is f of c. And big M is f of d. Next, I try to take a limit as h approaches to 0 for this function. And this function is the same as the middle function here. How to take a limit for this function here? Let me recall the squeeze theorem. That's what we learned in last semester. Squeeze theorem says if the functions f, g, and h are continuous at a, with f is less than g, g is less than h. If the limit as s approaches to a, f of x equal to L, and the limit as s approaches to a, h of x is also L, then the limit of the middle function must also be L. That's called squeeze theorem. If the limit from the left side function and the limit from the right side function is the same, then the limit from the middle function must also be the same. This is called the squeeze theorem. That's what we learned last semester. Let's apply here. Taking limit directly from the middle function is very hard. So let me take a limit from the left side function and right side function, see what we get. If they are the same, then by squeeze theorem, the middle function must also have the same limit. So let's take a limit here as h approaches to 0 for f of c. And take a limit here as h approaches to 0 for f of d. How do we take a limit here as h approaches to 0? How do we find the limit here? We know that c and d, they are both in the interval from x to s plus h. C and d, they are both in the interval from x to s plus h. Both c and d, they are here, between x and s plus h. So both c and d are here. C is between x and s plus h. Same thing, d is also between x and s plus h. Now, as h approaches to 0, what happened? As h approaches to 0, what happened? What happened to c and d? So, as h approaches to 0, let's apply squeeze theorem again here. Let's apply squeeze theorem. Taking limit directly for c and d is not easy. Let's take a limit for x and s plus h. As h approaches to 0, take limit from the left side and right side function. What happened? For the left side function, it's a function of x. So as h approaches to 0, it stays the same. This is equal to x. As h approaches to 0, it stays as x. For the right side function, as h approaches to 0, we get x plus 0, which is x. Since the left side function equal to the right side function, the middle function must also be x. So for both c and d, they must both be x by squeeze theorem. Both c and d must be x by squeeze theorem. So as h approaches to 0, c approach to x. as h approaches to 0, c approaches to x by squeeze theorem. As h approaches to 0, left side and right side function, they both equal to x. So the middle function must also be x by squeeze theorem. So by squeeze theorem, as h approaches to 0, c approaches to x, and similarly, d approaches to x. As h approaches to 0, both c and d approach to x by squeeze theorem. As h approaches to 0, both c and d approach to 0. Both c and d approach to x. When c approaches to x, I plug in x for c, so that's f of x. As c approaches to x, I plug in x for c. c approaches to x, I plug in x for c, I get f of x. As d approaches to x, I plug in x for d, I get f of x. As d approaches to x, I plug in x for d, so I get f of x. If left side function equal to the right side function, if the limit of the left side function equal to the limit of the right side function, then by squeeze theorem, the limit of the middle function must be the same as f of x. So by squeeze theorem, the limit as h approaches to 0, integral from x to s plus h, f of t dt over h equal to f of x by squeeze theorem, which means this limit equal to f of x. This limit equal to f of x. So g prime of x equal to f of x. We complete the proof. G prime of x equal to f of x. We complete the proof. So g prime of x equal to f of x. Hence, the derivative of the integral from a to x, f of t dt equal to f of x. That's the complete proof of the fundamental theorem of calculus. That's the complete proof. Next, let's look at some examples. Differentiate each of the following functions. First function, f of x, is the integral from 1 to x, 2t squared plus 1 times dt. How do we differentiate this function? By fundamental theorem of calculus, when we take derivative for integral, if the lower limit is constant, upper limit is a variable, we plug in a variable for t. If the lower limit is constant, upper limit is a variable, we plug in a variable for t. So we have 2x squared plus 1. When we take derivative for integral, the derivative undo the integral. The derivative undo the integral. So we plug in x for t. That's the answer. Next example. F of x is the integral from 4 to x, t to the power 3 minus 2t times dt. Take derivative for this function. Using fundamental theorem of calculus, for integral, when we take derivative for integral, if the lower limit is constant, upper limit is a variable, we plug in a variable for t. Plug in a variable, I get t cubed minus 2, I get s cubed minus 2x. Derivative undo the integral. Derivative of integral, the derivative undo the integral. So we plug in x for t. That's the answer for this one. Next, f of x is the integral from x to 3, 1 over t squared plus 6t times dt. How do we take derivative for this function? Here, the upper limit is a constant, lower limit is a variable. What should we do here? For integral, there's a property says, if I switch the upper and lower limit, I change the sign of the integral, make it from positive to negative. That's the property of integral. If I interchange the upper and lower limit, I change the sign of the integral. Then we can apply fundamental theorem of calculus. When we take derivative for integral, if a lower limit is constant, upper limit is a variable, we plug in a variable for t. So here, negative sign stays the same. Apply fundamental theorem for this integral, I get 1 over x squared plus 6x. Plug in x for t, and keep negative sign the same. Derivative undo the integral. That's fundamental theorem. Next, f of x is the function integral from x to -1, square root of t squared plus 5 dt. F of x is the integral from x to -1, square root of t squared plus 5 times dt. So, for this function, the lower limit is a variable, upper limit is a constant. If we try to take derivative, we need to interchange an upper and lower limit. One of the property of integral says, if I interchange an upper and lower limit, change the sign of the integral. So this integral can be rewrite as integral from -1 to x, square root of t squared plus 5 times dt. Then apply the fundamental theorem of calculus. When we take derivative for integral, the derivative undo the integral. Keep negative sign the same. Derivative undo the integral. We plug in x for t. Plug in upper limit for t. I get square root of x squared plus 5. That's the answer. Next example. F of x is the integral from 2 to x squared. T squared plus sine t dt. How do we take derivative for this function? Here, lower limit is a constant. In the integral, lower limit is a constant. Upper limit is not single letter. What should we do here? So how can we make single letter here? Here we can use chain rule. Let u equal to x squared. If we let u equal to x squared, then this is a single letter. And this is a function of u. And chain rule says, dy over dx equal to dy over du times du over dx. Let's chain rule. dy over dx equal to dy over du times du over dx. That means I first take derivative with respect to u, and then times du over dx. If I let u equal to x squared, now this is a function of u. In the function here, that's a single letter u. Then, by fundamental theorem, I plug in u for each t. U is x squared. Plug in u for each t, I get x squared squared plus sine of x squared. Plug in u for each t. Here, u is x squared. Plug in u for each t. This is dy over du, and then times du over dx. What's du over dx? Here, u is x squared. Du over dx is 2x. Derivative of x squared is 2x. So here we use chain rule. Plug in x squared for each t, and then times the derivative of x squared. So in general, when we use fundamental theorem of calculus to take derivatives, if an upper limit is not a single letter, we plug in upper limit first for the variable, and then times the derivative of an upper limit. And for the final answer, we can simplify. Write 2x in the front. We have x to the power 4 plus sine x squared. That's the final answer. Next example. F of x is the integral from 1 to 1 over x. Cosine of t plus t cubed dt. How do we take derivative for this function here? Again, in this function, upper limit is not a single letter. It's 1 over x. It's a function of x. So use chain rule. We plug in upper limit for each t. Plug in upper limit for each t. Okay, cosine 1 over x plus 1 over x to the power 3. Plug in upper limit for each t. Then times the derivative of an upper limit. What's the derivative of 1 over x? 1 over x can be rewritten as negative. It can be rewritten as x raised to negative 1. If I take derivative, I bring x negative 1 to the front. Subtract 1 from exponent. I get negative 1 times x raised to negative 2. So I plug in upper limit for each variable and then times the derivative of an upper limit. Then simplify the answer. That's cosine of 1 over x squared plus 1 over x cubed. This can be rewritten as negative 1 over x squared. That's the derivative of this function. Next, f of x is the integral from cosine x to 3 t squared plus 1 over t cubed dt. How do we take derivative from this function? Here, the lower limit is cosine x, upper limit is 3. First of all, we have to switch upper and lower limit. Bring the constant to the bottom here. Move lower limit, constant to lower limit. If I change the upper and lower limit, I change the sign of the integral, make it negative. Then use fundamental theorem of calculus. When we take derivative, we plug in upper limit for each variables, and then times the derivative of an upper limit. Here, the negative sign stays the same. I plug in upper limit for each variables. I get cosine of x squared plus 1 over cosine of x cubed. Then times the derivative of an upper limit. Derivative of cosine is negative sine x. So first of all, we plug in upper limit for each variables, and then times the derivative of an upper limit. Then simplify. Double negative become positive, and we can write sine x in the front. That's cosine square of x plus 1 over cosine cube of x. That's f prime of x. That's the derivative of this function. Next example. F of x is the integral from square root of x to 2 sine t minus cosine t dt. How do we take derivative from this function? In order to use fundamental theorem, I need to first of all interchange upper and lower limit. Make constant on the bottom and the function on the top, function of x on the top. And when I change the upper and lower limit, we need to change the sign of the integral. It's positive, we make it negative. Sine of t minus cosine of t dt. Next, when we use fundamental theorem to take the derivative, when we use fundamental theorem to take derivative, plug in upper limit for each t. plug in upper limit for each t, I get sine square root of x minus cosine square root of x, and then times the derivative of an upper limit. Square root of x can be rewritten as x raised to half. When we take derivative, I get half times x raised to negative half. Then if we simplify, we can bring this to the form negative 1 over 2 square root of x, bring this to the form, times sine square root of x minus cosine square root of x. So when we take derivative using fundamental theorem of calculus, plug in upper limit for each t, and then times the derivative of an upper limit. That's the derivative of this function. Next, f of x is the integral from 2x to 5x squared, 1 over t cubed plus 1 minus t squared times dt. How do we take derivative for this function? So for this function, for this integral, if both upper and lower limit contains x, in order to use fundamental theorem, we need to split this integral into two integrals. So first of all, we take integral from 2x to 0, 1 over t cubed plus 1 minus t squared dt, plus the integral from 0 to 5x squared, 1 over t cubed plus 1 minus t squared dt. Then we can try to use fundamental theorem to take derivatives. For the first integral, we have 0 on the upper limit, 2x on the lower limit. In general, we try to put constant on the bottom. So if I interchange the upper and lower limit, I change the sign of the integral. So it can be written as integral from 0 to 2x, negative of the integral from 0 to 2x, 1 over t cubed plus 1 minus t squared dt, plus the integral from 0 to 5x squared, 1 over t cubed plus 1 minus t squared dt. That's a preparation. Next, we can use fundamental theorem to take derivatives. Fundamental theorem of calculus says we plug in upper limit for each variables here. Plug in upper limit for each variables. I get 1 over 2x cubed plus 1 minus 2x squared, and then times the derivative of an upper limit, which is 2. So fundamental theorem of calculus says we plug in upper limit for each variables, and then times the derivative of an upper limit, which is 2. That's by chain rule. Negative sign stays the same. That's the first integral. Next, take derivative for the second integral. Take derivative for the second integral. Same thing. We plug in upper limit for each variables. We get 1 over 5x squared cubed plus 1 minus 5x squared squared times the derivative of an upper limit. 5x squared is 10x. So by chain rule and fundamental theorem of calculus, we plug in upper limit for each variables. Plug in upper limit for each variables, and then times the derivative of an upper limit. And then simplify. I can bring 2 to the front. I get negative 2 times 1 over ax cubed plus 1 minus 4x squared. Plus, here I can bring 10x to the front. Plus 10x times 1 over 125 x to the power 6 plus 1 minus 25 x to the power 4. That's the derivative of this function. Next, f of x is the integral from cosine of x to sine of x. Square root of t squared plus 4t dt. How do we take derivative for this function? If both the upper and lower limit contains x, we need to first of all split this into two integrals. First of all, take integral from cosine x to 0, square root of t squared plus 4t dt, plus the integral from 0 to sine x, square root of t squared plus 4t dt. So for the integral, I first of all take integral from cosine to 0, and then continue from 0 to sine. Let the sine is from cosine to sine directly. Then, in order to use fundamental theorem of calculus, I need to make a constant on the bottom. So in the first integral, interchange the upper and lower limit. If I interchange the upper and lower limit, I change the sign. I get negative integral from 0 to cosine x, square root of t squared plus 4t dt, plus the integral from 0 to sine x, square root of t squared plus 4t dt. Then we use fundamental theorem of calculus and chain rule to take derivatives. In the first integral, negative sign stays the same. And when we use fundamental theorem of calculus, we plug in the upper limit for each t. Plug in the upper limit for each t. I get square root of cosine square of t minus 4 plus 4 cosine square of x. Variable here is x. Cosine square of x plus 4 cosine x. Then by chain rule, times the derivative of the upper limit. Derivative of cosine is negative sign. Now for the second integral, plug in the upper limit for t. Plug in the upper limit for each t. I get square root of sine square of x plus 4 sine x. Then by chain rule, times the derivative of an upper limit. Derivative of sine x is cosine x. Then simplify. In the first term here, double negative become positive. I can write sine in the front. I get sine x times square root of cosine square x plus 4 cosine x. For the second term, I can bring cosine x in the front. I get cosine x times square root of sine square x plus 4 sine x. That's the derivative of this function. Next, let me introduce average value of a function. Suppose the function f is continuous on a closed interval from a to b. Then, the average value of function f on the interval ab is defined as f average equal to 1 over b minus a times the integral from a to b f of x dx. That's the formula for the average value of a function. But how does this formula make sense? Let me show you a picture first. Suppose function f is continuous on the interval from a to b. Assume that's the graph y equal to f of x. Assume that's the graph y equal to f of x. It's continuous on the interval from a to b. Here, f average, it can be rewritten as integral from a to b f of x dx divided by b minus a. 1 over b minus a times this integral is the same as saying this integral divided by b minus a. The integral from a to b f of x dx, it represents the area under the curve. it represents area under the curve from A to B, which means on the interval from A to B. What does B minus A represent? B minus A represents the width of the interval. The width of this interval is B minus A. B minus A represents the width of this interval. B minus A represents the width of the interval from B to A. If we take the total area under the curve, divided by the width of the interval. If we take total area under the curve, divided by the width of the interval, I can find the average height of the area. If I take total area divided by the width of the interval, I can find the average height of the area under the curve. That's how we define F average. Take total area divided by the width of the interval, we can find the average height of the area under the curve. That's how we define the average of a function. So F average is the total area under the curve divided by the width of the interval. That's the average height of all area under the curve. That's how we define F average. So F average is the average height of the function. On the interval from A to B. F average is the average height of the function on the interval from A to B. Next, let's look at some examples. For each of the following functions, find the average value on a given interval. First one, f of x is 6x squared plus 1 on the interval from 1 to 5. We know that the average formula is f average equal to 1 over b minus a times the integral from a to b f of x dx. That's the formula for the average value. So use the formula. F average is 1 over b minus a on this interval. That's a, that's b. So 1 over b minus a is 5 minus 1 times the integral from a to b from 1 to 5. 6x squared plus 1 dx. Then simplify. 1 over 5 minus 1 is 1 over 4. For this integral here, we take antiderivative first. I get 6x cubed over 3 plus x. Evaluate from 1 to 5. 6x cubed over 3 can be rewritten as 2x cubed plus x from 1 to 5. Then plug in 5, plug in 1, take the difference. If I plug in 5 cubed is 125. 125 times 2 is 250. 250 plus 5 is 255. If I plug in 1 cubed is 1. 2 times 1 is 2. 2 plus 1 is 3. 255 minus 3 is 252. And 1 over 4 times 252 is 63. That's the average value of the interval from 1 to 5. Next example, f of x is square root of x on the interval from 4 to 9. So use the average formula. F average is 1 over b minus a, 9 minus 4, times the integral from 4 to 9. F of x is square root of x dx. 1 over 9 minus 4. Here, 9 minus 4 is 5. So I get 1/5. Integral from 4 to 9. Square root of x can be rewritten as x raised to half dx. Then take antiderivative. Take antiderivative. Add 1 to the exponent. Divide by the new exponent. Evaluate from 4 to 9. A function divided by fraction means multiply by the reciprocal. So you get 1/5 times 2/3. A function divided by a fraction means we multiply by its reciprocal times x raised to 3/2. Evaluate from 4 to 9. Here, multiply the fraction. 1/5 times 2/3 is 2/15. Then here, plug in upper and lower limit and take difference. If I plug in 9 raised to 3/2 is 27. If I plug in 4 raised to 3/2 is 8. 27 take away 8 is 19. Then multiply, we get 38/15. That's the average value of the function on the interval from 4 to 9. Next example. F of x is sine x on the interval from 0 to pi/2. F of x is sine x on the interval from 0 to pi/2. So use the average formula. F average is 1 over b minus a. Here is pi/2 minus 0. Times the integral from a to b, from 0 to pi/2. Sine x dx. Simplify this expression first. Pi/2 minus 0 is pi/2. 1 over pi/2 is the reciprocal, 2 over pi. Here, pi/2 minus 0 is pi/2. 1 over pi/2 is the reciprocal, 2 over pi. Next, take this integral. I first of all take antiderivative for sine x. Antiderivative of sine x is negative cosine x. Evaluate from 0 to pi/2. If I plug in pi/2, cosine pi/2 is 0. If I plug in 0, cosine 0 is 1. 0 minus negative 1, double negative is positive. So I get 2 over pi times 1. 2 over pi times 1 is 2 over pi. That's the average value of the function on the interval from 0 to pi/2. Next example. F of x is the function secant square x on the interval from pi/6 to pi/3. How do we find the average? Use the formula. F average is 1 over b minus a. pi/3 minus pi/6 times the integral from a to b, from pi/6 to pi/3. F of x dx. Here f of x is sine square x, secant square x dx. Simplify this part first. On the denominator, pi/3 minus pi/6. They have different denominator, so we need to find common denominator first. For pi/3 and pi/6, common denominator is 6. So on the first fraction, I can multiply top and bottom by 2. I get 2 pi over 6 minus pi/6. 2 pi over 6 minus pi/6 is pi/6. And 1 over pi/6 is 6 over pi. Let me take care of this number first. Next, take antiderivative to the function. For secant square x, its antiderivative is secant x. It's tangent x. For secant square x, its antiderivative is tangent x. Then evaluate from pi/6 to pi/3. Evaluate from pi/6 to pi/3. I first of all plug in pi over 3. Tension pi over 3 is radical 3. Then I plug in pi over 6. Tension pi over 6 is 1 over radical 3. Now here, how do we simplify? Radical 3 minus 1 over radical 3. Let me simplify here. Radical 3 minus 1 over radical 3. First step, we need to rationalize the denominator. So we multiply the top and the bottom by radical 3. Rationalize the denominator first. I get radical 3 on the top, 3 on the bottom. Next, I rewrite the first number as radical 3 over 1 minus radical 3 over 3. Then find the least common denominator, which is 3. So I can multiply top and the bottom by 3. I get 3 radical 3 over 3 minus radical 3 over 3. Now the same denominator. Keep denominator, subtract the numerator. 3 radical 3 minus radical 3 is 2 radical 3 over 3. So I simplify this. I get 2 radical 3 over 3. 6 over pi stays the same. If I simplify, I can cancel 3 from top and the bottom. Cancel 3 from top and the bottom, I get 2 on the top. 2 times 2 radical 3 is 4 radical 3 over pi. That's the average of the function on the interval from pi over 6 to pi over 3. Next, f of x is 1 over x squared. Find average on the interval from 1/3 to a half. F of x is 1 over x squared. Find average on the interval from 1/3 to a half. So use the average formula. F average is 1 over b minus a. That's a, that's b, so use b minus a. 1 over 2 minus 1 over 3 times the integral from a to b, from 1/3 to a half. F of x times dx. Here f of x is 1 over x squared times dx. Let's simplify this number first. 1/2 minus 1/3. Common denominator is 6. So for the first fraction, I can multiply top and the bottom by 3. For the second fraction, I multiply top and the bottom by 2. So I get 3 over 6 minus 2 over 6, which is 1 over 6. And 1 over 1 over 6 is 6. Let me simplify this number first. Then take care of the integral. 1 over x squared can be rewritten as x raised to -2. Then take antiderivative. When we take antiderivative, add 1 to the exponent and divide by the new exponent. Evaluate from 1/3 to a half. Let me simplify this first. This fraction can be simplified as -1 over x. I bring x from top to the bottom, make exponent positive, and pull out negative sign. -1 times 6 is -6. So I get -6 here. 1 over x. Evaluate from 1/3 to a half. Then plug in a half, plug in a third. If I plug in half, 1 over a half is 2. If I plug in a third, 1 over a third is 3. So I got -6 times 2 minus 3, which is -1. -6 times -1 is +6. So that's the average value of the function on the interval from 1/3 to a half. Next example. F of x is cosine of x. Find average of the interval from pi over 2 to 3 pi over 2. f of x is cosine x for an average of the function on the interval from pi over 2 to 3 pi over 2. So here let's use an average formula. F average is equal to 1 over b minus a, which is 3 pi over 2 minus pi over 2, times the integral from a to b, from pi over 2 to 3 pi over 2. F of x is cosine x times dx. Let me simplify this number in the front first. 3 pi over 2 minus pi over 2 is 2 pi over 2. 2 pi over 2 is pi. So I get 1 over pi. Then for this integral here, I first of all take antiderivative. Antiderivative of cosine is positive sign. Evaluate from pi over 2 to 3 pi over 2. Then plug in 3 pi over 2 and pi over 2, take difference. Sine 3 pi over 2 is negative 1. If I plug in pi over 2, sine pi over 2 is 1. Negative 1 minus 1 is negative 2. So you get 1 over pi times negative 2. 1 over pi times negative 2 is negative 2 over pi. That's the average value of this function on the interval from pi over 2 to 3 pi over 2. Next, we will study the mean value theorem for integral. First of all, let me recall the mean value theorem for derivative. That's what we learned last semester. The mean value theorem for derivative says, if function f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists a real number c between ab, such that f prime of c equal to f of b minus f of a over b minus a. And this equation is equivalent to b minus a times f prime of c equal to f of b minus f of a. That's mean value theorem for derivative, and that's what we learned last semester. Today, I'll show you the mean value theorem for integral. The mean value theorem for integral says, suppose f is continuous on a closed interval ab. Suppose f is continuous on a closed interval ab. Then there exists a real number c there exists a real number c between ab, not including ab. There exists a c between ab. ab is not included. Such that f of c equal to f average, such that f of c equal to f average, which is 1 over b minus a times integral from a to b, f of x dx. That's the mean value theorem for integral. Suppose f is continuous on a closed interval ab, then there exists a real number c between ab, not including ab, such that f of c equal to f average, which is 1 over b minus a times integral from a to b, f of x dx. That's the mean value theorem for integral. In order to understand the mean value theorem better, let me show you a picture. Suppose function f is continuous on the interval ab. Assume that's the graph of function f. Y equal to f of x. It's continuous on the interval ab. A is here, b is here. Assume function f is continuous on the interval ab, and assume f average is here. F average represents average value of function f on the interval ab. Assume that's f average. The mean value theorem of integral says there exists a real number c between ab, such that f of c equal to f average. Mean value theorem says there's a real number c between a, b, such that f of c equal to f average. So there's a real number c between a and b, such that f of c equal to f average. That's what its mean value theorem says. Suppose function f is continuous on the interval a, b, and suppose f average is here. Then, by the mean value theorem, there exists a real number c between a and b. There's a c between a, b, such that f of c equal to f average. Let me show a different picture. Suppose this graph of function f. Function f is continuous on the interval a, b. Suppose a is here, b is here, f average somewhere here, for example. That's the average value of the function on the interval a, b. Suppose f average is here. Mean value theorem says there's a real number c between a, b, such that f of c equal to f average. So here, c could be here, or it could be here. There are two choices for c. Let's call it c1, call it c2. There is a real number c, it could be more than one. There is a real number c between a, b, such that f of c equal to f average. Here, f of fc1 equal to f average, and fc2 also equal to f average. It could be more than one c. Next, let's prove the mean value theorem for calculus. Let's prove it. Since f is continuous on the interval a, b, let function g be defined as integral from a to x f of t dt for all x between a and b. Since f is continuous, I can define function g as the integral from a to x f of t dt for all x in the interval from a to b. Then, by the fundamental theorem of calculus, if I take derivative for g, what do we get? By fundamental theorem of calculus, if I take derivative for g, I plug in upper limit for t, I get f of t. I get f of x. Plug in upper limit for t, I get f of x. So, by fundamental theorem of calculus, g prime of x equal to f of x. Since the derivative of function g exists, we say function g is differentiable. Since the derivative of function g exists, we say function g is differentiable. Function g is differentiable on the interval from a to b. Since function g is differentiable on the interval from a to b, then it must be continuous on the same interval. Because whenever the function is differentiable, it must be continuous. So, hence, g is continuous on the same interval. On the interval from a to b. Now, since function g of x is continuous on a closed interval and differentiable on the open interval AB, because function g is differentiable on a closed interval. The open interval is a subinterval of this interval, so it must also be differentiable. Since g is continuous on a closed interval, differentiable on the open interval, then by the mean value theorem for derivative, there is this real number c by the mean value theorem for derivative, there is a real number c between a and b, such that f prime of c equal to, here is function g, so it be g prime of c. Here we use function g here, so it will be g prime of c equal to g of b minus g of a over b minus a. That's the mean value theorem for derivative. In general, we use function f prime of c equal to f of b minus f of a over b minus a. Here we use function g. So since g is continuous and differentiable, then by mean value theorem, there's a real number c, such that g prime of c equal to g of b minus g of a over b minus a. That's the mean value theorem for derivative. Next, let me simplify this formula. What's g of b? What's g of b? For g of b, we plug in b into function g for every x. Plug in b into function g for every x. So I get integral from a to b f of t dt. Integral from a to b f of t dt. What's g of a? G of a, I plug in a for each x on function g. Let's integral from a to a f of t dt over b minus a. And it can be rewritten as, I leave the first integral the same. Integral from a to b f of t dt. What's the integral from a to a f of t dt? Integral from a to a f of t dt, it represents area under the curve from a to a. If we take integral under the curve, if we find area under the curve from a to a, there's no area. So this integral is 0. If we try to find area under the curve from a to a, there's no area. So this integral is 0. Integral from a to a f of t dt is 0 over b minus a. And then this integral can be rewritten as 1 over b minus a times the numerator. In the numerator, this integral minus 0 disappear. We have integral from a to b f of t dt. And in general, f of t dt is the same as f of x dx. In general, f of t dt is the same as f of x dx. Because for f of integral from a to b f of t dt, we take antiderivative for function f, then plug in upper limit and lower limit take difference by evaluation theorem. Take antiderivative for function f, we get capital F, then plug in upper limit and lower limit and take difference. That's integral from a to b f of t dt. And for integral from a to b f of x dx, we do the same thing. Take antiderivative for function f. We get capital F. Then plug in upper limit and lower limit. We get f of b minus f of a. So they are exactly the same. Integral from a to b f of t dt and integral from a to b f of x dx. They are exactly the same. So this is the same as integral from a to b f of x dx. And this is the average. This is f average. This is f average. So g prime of c equal to f average. There's a c between a and b. There's a c between a and b such that g prime of c equal to f average. Since g prime of x is f of x, then g prime of c is the same as f of c. So f of c equal to f average. Since there is a c between a and b such that f of c equal to f average, that complete the proof for the mean value theorem. Next, let's look at an example here. For each of the following functions, find c that satisfies the conclusion of the mean value theorem for integral on a given interval. First example, f of x is x squared minus x minus 2 on the interval from 0 to 6. That's the conclusion of the mean value theorem. F of c equal to f average. We try to find all c's such that f of c equal to f average. So let's find f average first. F average is 1 over b minus a. Here is 6 minus 0 times the integral from 0 to 6 f of x dx. Here f of x is x squared minus x minus 2 times dx. Here 1 over 6 minus 0 is 1 over 6. Solve this integral. We first of all take antiderivative. We get s cubed over 3 minus s squared over 2 minus 2x. Evaluate from 0 to 6. If I plug in 6 cubed is 216. 216 over 3 is 72. If I plug in 6 here, 6 squared is 36. 36 divided by 2 is 18. If I plug in 6 here, 2 times 6 is 12. Next, plug in 0. If I plug in 0, I get 0, 0, 0, which is 0. Then here, 72 minus 18 is 54. 54 take away 12 is 42. 1 over 6 times 42 is 7. So f average is 7. Next, we set the function f of x equal to 7. Next, set the function f of x equal to 7. Set the function f of x equal to 7. So we have s squared minus x minus 2 equal to 7. Then solve the equation for x. Here I can subtract 7 from both sides. I get s squared minus x minus 9. Set equal to 0. Then solve this equation using quadratic formula. Solve this equation using quadratic formula. We have s equal to negative b plus or minus square root of b squared minus 4ac over 2 times a. Simplify, I get positive 1 plus or minus square root of 1 plus 36 over 2. So s equal to 1 plus radical 37 over 2, or 1 minus radical 37 over 2. Next, I use my calculator to find these two values. 1 plus radical 37 over 2 in my calculator is about 3.54. And 1 minus radical 37 over 2 in my calculator is about negative 2.54. Since c must be between a and b, in this case, c must be between 0 and 6. Since negative 2.54 is not between 0 and 6, it doesn't count. Only 3.54 is between 0 and 6. So C must be this number. Since only 1 plus radical 37 over 2 is between 0 and 6, then C must be this number, 1 plus radical 37 over 2. So that's an answer. We find C. Let's satisfy the conclusion of the mean value theorem. If I plug in C here, I get f of C equal to 7. If I plug in C here, I get f of C equal to 7. And 7 is an f average. So we have f of C equal to f average. So C is between A and B, such that f of C equal to f average. That satisfies the conclusion of the mean value theorem. That's an answer to this problem. Next, f of x is sine x. Find C. Let's satisfy the conclusion of the mean value theorem on the interval from pi over 2 to 2 pi. First step, we find f average. Let's find f average first. The formula for f average is 1 over b minus a, 2 pi minus pi over 2. 1 over b minus a times the integral from a to b, from pi over 2 to 2 pi. F of x dx. Here f of x is sine x times dx. Then let's simplify this number first. 1 over 2 pi minus pi over 2. 2 pi minus pi over 2 is 3 pi over 2. And 1 over 3 pi over 2 is the reciprocal, 2 over 3 pi. That's the number in the front. Next, let's take antiderivative for this function. Antiderivative of sine x is negative cosine x. Evaluate from pi over 2 to 2 pi. If I plug in 2 pi, cosine of 2 pi is 1. Keep negative sign the same. Minus, if I plug in pi over 2, cosine pi over 2 is 0. Negative 1 minus 0 is negative 1. Negative 1 times 2 over 3 pi is negative 2 over 3 pi. That's f average. Next, we set the function set f of x equal to f average. Set f of x equal to f average. F of x is sine x equal to negative 2 times negative 2 over 3 pi. Then in order to solve for x, use inverse sine function. X is inverse sine of negative 2 over 3 pi. Then I use my calculator. Inverse sine of negative 2 over 3 pi in my calculator is about negative 0.213a. Is this number in the interval from pi over 2 to 2 pi? We know that pi is 3.14. 3.14 divided by 2 is about 1.57. And 2 times 3.14 is about 6.28. Is this number in the interval from 1.57 to 6.28? This number is negative, so it's not in the interval from 1.57 and 6.28. Then what's wrong here? Mean value theorem says there must be a C between the interval a, b. But here we don't see any C between this interval. Did we make any mistake? Be very careful. For trig functions, if we use inverse sine in the calculator, we don't get all the solutions. For trigonometry functions, if we solve in the calculator, we won't get all solutions. So for trig functions, usually we have to solve it manually. For trig functions, if we solve in the calculator, we won't get all solutions. So for trig function, we need to solve it manually. How do we solve this manually? First step, find a reference angle. First step, find a reference angle. That's a review for pre-calculus. Find the reference angle. For the reference angle, we take inverse sine of 2 over 3 pi. If reference angle is always positive, we take inverse sine of 2 over 3 pi. Reference angle is always positive, so drop negative sign. And this number in the calculator is about positive 0.2138. That's a reference angle. Find a reference angle first. And we know that sine function is positive in quadrant 1 and quadrant 2, negative in quadrant 3 and quadrant 4. Sine function is positive in quadrant 1 and quadrant 2, negative in quadrant 3 and quadrant 4. We need to find actual angle from quadrant 3 and quadrant 4. Since sine here is negative, since sine function is negative, we need to find actual angle in quadrant 3 and quadrant 4. We know that in the first quadrant, the reference angle is the same as the angle itself. In the first quadrant, reference angle is the same as the angle itself. We use S bar represent reference angle. With theta bar represent reference angle. Theta represent actual angle. In quadrant 2, this is pi here. Reference angle is pi minus theta. In quadrant 2, reference angle is pi minus theta. In quadrant 2, reference angle is pi minus theta. In quadrant 3, reference angle is here. It's theta minus pi. In quadrant 3, reference angle is theta minus pi. In quadrant 4, that's reference angle. 2 pi is here. So in quadrant 4, for the reference angle, we take 2 pi minus theta. That's reference angle in different quadrants. We're looking for actual angle. So for actual angle in the first quadrant, it's the same as the reference angle. For the actual angle, theta, in the second quadrant, if I solve this equation for theta, theta equal to pi minus theta pi, equal to theta bar. Theta equal to pi minus theta bar. That's a reference angle. For angle in the third quadrant, solve the equation for theta. Solve the equation for theta. Theta equal to pi plus the reference angle, theta bar. Then for the actual angle in quadrant 4, theta is 2 pi minus the reference angle. That's how we find actual angle based on reference angle in different quadrants. So the first line is how we find reference angle on each quadrant. Second line is how we find actual angle based on reference angles in different quadrants. Here we know the reference angle is 0.2138. For the actual angles, this sine function here is negative. We're looking for the actual angle in quadrant 3 and quadrant 4. Since sine is negative, we're looking for the actual angle in quadrant 3 and quadrant 4. So for the actual angle in quadrant 3 and quadrant 4, we use pi plus the reference angle in quadrant 3 and 2 pi minus the reference angle in quadrant 4. So for the angle in quadrant 3, we use pi plus the reference angle. Reference angle is inverse sine of 2 over 3 pi. That's the angle in quadrant 3. For the angle in quadrant 4, we have sine. We have 2 pi minus the reference angle. We have 2 pi minus the reference angle. Then I use my calculator. Pi plus inverse sine of 2 over 3 pi is about 3.36 in my calculator. And 2 pi minus inverse sine of 2 over 3 pi in my calculator is about 6.07. Here, both solutions, they belong to this interval. So they are both C values. They are both C's. So C could be either pi plus inverse sine of 2 over 3 pi, or C could be 2 pi minus inverse sine of 2 over 3 pi. They both belong to the interval. which means if I plug in c here, f of c equal to this number, and this number is f average. That means there's a c in the interval from a to b such that f of c equal to f average. That satisfies the conclusion of mean value theorem.